So if you could give it to Tristan. Apparently the other one is, yes. Yes, all right, so, while the microphone borrow and swap is going on, yes, I'll transition us to the second talk. So when I think about Tristan, I think about scale. So Tristan describes himself as passionate about binary analysis. Not sure a sentence I can fully comprehend, but of course that's something that requires immense scale to doing static analyses because binaries are so large. And Tristan worked in binary analysis for about a decade during his PhD at University of Wisconsin and at Galois. But now he's taking this sort of to the next level at Amazon, where he's part of the automated reasoning group, and where he's looking to apply analyses on security properties for the services that power the internet, billions of requests per second. And I think hearing how the work we do can be scaled up in this important industrial context is what I'm most excited about in this talk. So Tristan, please take it away.
Thank you. Great timing. That was just enough to get all the display stuff worked out. So yeah, I'm going to be talking about some of the work we're doing in AWS in particular, but also used across the rest of Amazon too, if you're curious, on automating some evaluation of security properties and also like the sort of compliance assurance angle, if that kind of thing interests you. And the title is impenetrable, and I think it will make a little bit more sense as we go along. But I'll just tell you the takeaways now, and then you can tune out if you want. But we're using automated reasoning at scale to analyze all the services in AWS and build models of those systems so that we can do cross-service, cross-AWS analysis of security properties. And we're using those models to drive some of the other security tools that have been around and really powerful tools for a long time, but tools that required a lot more hands-on work from domain experts. And now we are using this automatic context inference to get to a place where we don't need to ask people questions. We can actually just answer security questions for them on their behalf. And then I'm going to go into some of the little details that never make it into papers, but that really matter when you're trying to analyze real code made by very clever engineers. There are some things I won't cover here. Scale, which is funny to say. We're talking about the scale of analyzing everything, but I'm not going to be talking about the scale of what do we do to scale up the individual like data flow analyses. That's really important, obviously, and one could imagine a whole separate other hour-long or so talk about that topic. And there was actually one earlier this week at SOAP by Michael Emmy. I think he's around if you have some questions on that. And I hope it will be recorded so you can actually see some of the algorithmic things we do to make this work at scale, the other kind of scale. But the background here is that the goal I have in this work is to be able to prove security properties continuously for everything in AWS and without having to ask any of our developers any questions about like what they're doing, what did they mean to do, what does their code currently do. These are all things that we can handle with automation now. So some example properties before we get into it, things like proving properties about data storage. We want to be able to prove and generate evidence for the fact that data is stored where we expect, when we expect it, and with the right levels of access. And ultimately, that's a graph reachability problem. Or at least it would be if you had a graph. Again, we don't want to have to ask anyone to build this graph for us, so we're going to build it. There's also a whole family of properties, and this is not exhaustive, this is just indicative, but things like proving that services are configured with least privilege access. There's a very powerful permissions mechanism for controlling what different services have access to and at what times. And we want to always make sure and to be able to provide evidence that each one of those services has only the permissions it needs and no more. So if you have a service that has been given a set of permissions, that's like an IAM role, you can also imagine that there's a set of permissions that it actually uses. And in this, I've labeled those as P1 and P2. The problem of proving these privileges is proving that P1 equals P2. And I'll have some examples later, but what we really want to do here is get P1 automatically and also calculate what P2 is without asking anyone what P2 is. And then once I have that, I have access to this other very powerful tool. All AWS customers do, IAM Access Analyzer, that reduces questions about permissions down to SMT, and that lets us automatically answer these questions if we can get P2. So we need models of our systems to be able to answer these questions, to get this context so that we can actually answer these with automation. And that gives us sort of the operational context. So the model will tell us where things are executing, what they have access to, how they do their jobs. And if you're thinking about models, often you might see something like this. People will draw a picture, and a picture is a good way to view a model, but it's rarely that easy. But this is an example of a picture that I would draw for the system that is sort of like the notional system for this talk. It doesn't do anything in particular that's interesting, but it gets across this idea that what I'm analyzing is an AWS account, which is full of resources and full of compute. The compute are the orange things, that is where your code runs and does things with the data in the account. You can see that the requests enter this system because it's a web service. Requests enter on the left-hand side. They are routed to a piece of compute that logs data. It sends data to an object store. It sends data to a database. All the usual kinds of things you would expect. This is a nice picture. And if you built this system, you could draw this picture. But if someone gives you an arbitrary system or gives you thousands of arbitrary systems that you don't know anything in particular about, it looks a little bit more like this. It is a collection of things, and you have to figure out or recover what they're doing. So that's what this talk is about, recovering a model from that. So what we're going to do is use automated reasoning to do this. There are going to be 3 steps, 2.5 steps. I don't know how you want to count it. We're going to start off by analyzing the infrastructure in that account, just having it describe itself. Then we're going to analyze the code. That should be unsurprising given the venue. And then we're going to combine those things into one merged system model. One nice thing about working in this domain of web services and like an AWS account full of resources, it's self-describing. You can actually go and probe the account and ask it to list off all the resources in the account. And moreover, you can actually get each of those resources to tell you how it's configured. And that's really useful all by itself. So if you just ask this account, hey, what's going on? What's in there? How is it configured? You can reconstruct part of the model on the right-hand side. And you can get some reasonable details here, like the purple thing at the top on the top right. That's a database that's plumbing or piping some data to what's called a Kinesis fire hose. That lets you transform the data and then make copies of that data into other data stores. You can see that there's already some information about requests coming into the system through that API gateway being routed to a Lambda for processing. You can see that Lambda logs some data there. So that's part of the model we wanted. And that's pretty cheap. This is very easy. You don't have to think very hard to do this. But you'll notice that there are some gaps compared to the picture that was there before. And of course, those gaps are the orange parts. That's where the code is running. This is really important to understand the behavior of a system, though. You need to know what the code is doing because the code is receiving requests, picking data apart, combining it in new ways, transforming data, putting that data into new places, interacting with other systems. That's where the really interesting parts of your system happen. And to do that, you actually have to analyze the code. And we don't want to run this code to figure out what it's doing. That would be just logistically really hard. But we can use static analysis. So surprising no one, or no one here at least, this is abstract interpretation. We're going to use static taint analysis. And what I want to build here is a data flow map. And to do that, I'm just going to label every input, every field of every input to all of the services I have access to. And then I'm going to use static taint analysis to say, where does that data go? And that lets me collect this set of connections that are induced by the code that's actually running on the systems. And that gets me a nice little bipartite graph that is the map from inputs to outputs of what the code is doing with its data. And then that lets me complete the picture. So I had the previous picture from just analyzing the infrastructure. Now I can add in the edges that arise from the actions of the code itself. And because it's abstract interpretation, I get some nice bounds on execution time. I can run it on everything. I don't have to worry about how do I actually take an unknown piece of code and run it as it would run in production. I can just evaluate what it's going to do over all possible paths with a sound over approximation. Now, this is where you would probably want to look into the other talk for some of the details. There's a lot going on here where, this is a whole program analysis. And when you want to do a whole program analysis over all of your dependencies, you can easily run into the millions of lines of code. So there's some really fun scaling challenges. To get the precision we want, we end up needing at least object sensitivity, and we end up finding interesting patterns that need to be handled in exciting ways, because even just going with object sensitivity by itself isn't quite enough. We have to support multiple programming languages, because inside of Amazon, pretty much every programming language has its place. We have to do some interesting work to model things like reflection. So a lot goes into this part of the stack analysis, but that's not where I want to focus this talk. I just want to say, now that we have all that information, we can go back and build that model. This is roughly the model you would get if you asked an expert to go build or to draw the model of how they understand their system. I have actually done some work here to collapse all those edges. There's a lot more detail here because we're tracking things at the level of individual fields. But if you draw all of that, it turns out that the diagrams get pretty useless because there are too many edges. So we go with the simple one when we're drawing it for exposition purposes. But under the hood, this is not a picture. This is actually a data structure that you can then start automating security questions on. So like I talked about before, that includes our graph reachability problems over the full AWS stack. And then also going back to the least privilege question, I can fill in some of the details I glossed over. So again, least privilege in this context is us wanting to provide evidence that when a service has a set of permissions granted to it, it uses all of those permissions. It's not over-provisioned in terms of permissions. So I can get the IAM policy that grants those permissions on the left. Those are the ones that has actually been granted. And I can construct the policy on the right that describes what it actually does. And this is what it can do on all possible paths of execution, because we have a sound over approximation thanks to our abstract interpretation. And then I can use that to feed this other tool, IAM Access Analyzer, which turns these two policies into an SMT query that proves that they are, in fact, the same policy. And in this example, they are not. You can see that there is an extra permission that it has access to that it doesn't actually use. And that would be something that you would want to change by modifying the role assigned to it so that it is actually running with least privilege. And because this is all automated, we can do this for everything, which is great. And we've done it without asking anyone any questions, which is even better. But now the more fun part of the talk, for me, is that the devil is in the details. All of those things kind of follow from the sort of standard algorithms that you would imagine in the world of data flow analysis, abstract interpretation, taint analysis. But then there are the things that never make it into the papers or into the textbooks, at least not that I have seen. Just the engineering you need to do around the edges to really understand these systems. And I'm going to focus on two things. This is not exhaustive, but configuration and serialization. So I find this exciting. This is where we end up spending a surprising amount of time because we need to handle this for all of the interesting cases that we run into. So I've written on the slide that this is the complexity of real code. This is not real code. This is completely made up code, but it is indicative of what you would see in a typical web service. It is running in some sort of web service. It takes a request object, and you can see in the orange, it uses some information from that request to go fetch data from a database in the call to get item, and then it constructs a new piece of data, and it puts that into an object store in the call to put object. And that's great. Just by looking at this with a normal static analysis, we would be able to see that it is interacting and pulling data from the database and putting object into the object store. But that's not what we really want to know. What we really want to know is which object store, because if you have 50 different object stores, building a data flow map that just tells you that the data goes into an object store, that's not very useful. You need to know which one. And that's the data that I've highlighted in green, which is a very interesting green on this screen. But it's the name of the database table and the name of the bucket that's the data is being stored into. Those are what we really need. And you might say, well, just use constant propagation. And you're right. You're partly right. But the challenge is that it's not actually in the code at all. These things are set early in the execution of the program, often when it started, but the values aren't in the program. They come from configuration files. They come from the environment variables. Sometimes those environment variables are set by shell scripts. So you have to understand everything in the environment to be able to fill in these values. And that's actually what we do. We have code that runs before the analysis that analyzes the execution environment and introduces the constants that are introduced into the system at runtime, and introduces those statically at static analysis time by interpreting the environment. So that's like pulling configuration files, parsing configuration files, pulling environment variables that are configured for lambdas, doing things like analyzing shell scripts to figure out what are environment variables actually set to, doing the analysis in the context of different regions because you might have different values in different regions. So you might have to analyze the one running on the East Coast versus the West Coast versus Europe with the different values to really understand in each of those contexts what is being done. But once we have that data, we can introduce those constants and then just use constant propagation like you would expect to get the results we want at all of the data syncs. So again, at this get item call and the put object call, now we have that context we need, the name of the bucket, the name of the table, and we can build the data flow map that I showed before. There's another really fun example, and I didn't appreciate this one as much when I started this project, but I definitely appreciate it now. This is just a slightly modified version of that code snippet from before. I've got a request coming in. I pull some data out of that request, and I assemble a new piece of data, the thing in blue. It doesn't really matter what it is here, but it's basically a 3-tuple of some of the input data, some fresh data that's coming from this timestamp. And then what am I doing? I'm putting it through something that happens billions of times a day, maybe trillions, all up across the system, but I'm serializing it as a JSON value, and I'm storing it in an S3 bucket. Well, that seems pretty straightforward. And if you just think about what taint analysis would do here, just like a normal taint analysis, you would say, well, that string that is being stored in S3 has 3 different taints in it, or maybe 2 if you're just tracking the account ID and user data. And that's true, but it's not the most useful because now the other part of this is that someone else, some other service, is going to pull this data out of the S3 bucket and do something with it. And I really want to know which of those pieces of data are they using and where did it come from. And if I've smashed them all together into just a string, I lose that information. I think you might just say that they're using all of that data, and that's too imprecise. That means you'll start you might start seeing that user data appear in places that it's not actually used because maybe the data consumer is only pulling out one of the fields or 2 of the fields, but not the user data. And you don't want to have any sort of false report that, or some imprecise report that the user data is somewhere you don't want it. So where we end up here is that we actually have a lot of extra work inside of the taint analysis to be able to retain this structure. So this is really special handling for different kinds of serialization libraries and deserialization libraries because we need to be able to do this symmetrically on the other side of the system when we build the model. So it is in some sense unsurprising, but it is also almost as much work as the rest of the analysis by itself in some ways. So we end up having models of the different serialization libraries used across the whole system so that we can do this level of precise reasoning. I could probably go on all day, but I'll save some time for questions. The most important part of this slide is that we are hiring. And if you're curious, you could scan that QR code. We also have a booth or a table out in the lobby. But from this talk, I just want to again, remind you that what we're doing is using automated reasoning to build models of all of the systems in AWS so that we can do this security analysis continuously. And while you're doing this, it is really interesting to see what what you need to do that doesn't make it into the papers, and you might think that it's not that interesting, but it's really that last mile of work is critical to getting the types of results you need to get precise answers across the whole fleet.
Thank you, Tristan. So again, let's take questions at either microphone. I think both work. And we have time for
Do you ever show these models to developers? Because I expect they'll, one, be able to spot issues with them, but also might find them useful as like dynamically generated documentation.
Yeah, absolutely. Lots of people want to see the models because often, when you design a system, you build a model like this and you say, yeah, this is what we're going to build, and then you go build the system. And then no one ever updates that. So yeah, people are absolutely excited to see this type of model and check their understanding, use as onboarding material for new hires, because if it is pretty frustrating to join and then get shown some documentation that is very out of date and not understand, like, oh yes, this is what it looks like now. Being able to have that handy is great.
So you don't show it to them yet, but you're hoping to.
Oh, we've shown some. It's not something that we give to everyone and say, here is your system, but when people ask, yeah, we absolutely share them.
Thanks. Yeah, that was interesting. So you talked about mainly how to find out what the ground truth, what the code is doing. How do you figure out what properties you want to check about the code?
So what properties we want to check? Well, there are, from the security perspective, there are all sorts of properties that we always have in mind. They're universally true for all of the systems. So those are kind of like, I think of them as free properties. They have to be true. And then there's some other work going on where I'm in the process of building out more tailored specifications to each of the other services. So those give rise to other properties you would want to check that don't necessarily apply to every system, but apply to the ones where you know what they're supposed to be doing.
Right. Okay. So you're not, at least in this project, you're not mining the specifications. You have general specifications, or you're getting them from a separate source, basically.
Yeah. So not mining specifications right now, not as such, but one really good source of those specifications that I would like to explore more is just straight up the public documentation. Each service makes promises about what it does. That gives you derived specifications that get to filter down through the rest of the system.
Right. Thanks.
Hi, good talk. Just curious, like for more dynamic languages or languages with more metaprogramming, it seems kind of hard to catch statically all these different relationships. And I'm curious if you do any sort of dynamic verification, actually instrumenting to see like if any of you haven't caught any of the paths.
We haven't done any dynamic analysis. So we're confident that we can compute an over-approximation, but to your point, the over-approximation might be unpleasantly large for some kinds of languages. And actually my preference is, if something is too dynamic and too wild, I would rather say I don't know than give a very over-approximate answer. But there are some really interesting avenues to do some mixed dynamic refinement. So there is a thing, I think it's a service, a feature, I don't know. It's called X-ray, and it actually gives you a trace of calls through, like if you issue a call, it'll tell you like what other calls are being made on your behalf to service it. So that's one place where you could actually do some validation against a ground truth of observations, and that's sort of an under approximation that might help. It might help.
Thank you.
Okay, let's do another round of applause. Okay, that concludes our industry session. I want to call out that both John and Tristan will be here. You can find the booths right outside in the lobby. I'm sure many of you have additional further questions you'd like to ask. And now let's please go to the lobby, and I think we have student research competition finalists as well.